This training module describes the NOAA CIMSS Prob Severe statistical model, provides examples of the model output in AWOPS 2, and briefly discusses model validation and model limitations. Why do we need a statistical model to nowcast severe weather? The uses of statistical models are becoming more and more important and commonplace as data volumes explode in all aspects of our lives. Statistical models are used with great success to predict things like presidential elections and the outcomes of the NCAA basketball tournament. Meteorology is no different. As bigger and more frequent data becomes available to forecasters, it becomes more important to distill gigabytes of data into kilobytes of useful information. That is what the NOAA CIMSS Prob Severe model does. The Prob Severe model is a statistical model that employs numerical weather prediction environmental information, satellite observations, and radar observations. Before a brief discussion of the statistical model and data used, it is critical to define the objectives of the model. In this image you can see a developing strong thunderstorm. The statistical model is designed to predict in a probabilistic manner that a given developing storm will first produce severe weather in the next 60 minutes. In the example shown, the developing storm has a 60% probability of first producing severe weather in the next 60 minutes. The model is not designed to predict if a given storm will continue to pose a severe threat once it has been warned and/or is producing severe weather, and it is not designed to forecast storm decay. It is important to use the model output as a pre-polygon product. There may be utility in using the model probabilities past issuance of the first severe warning, but the model was not designed for this purpose and has not been validated in such a manner. Every detail of the statistical model is not important for understanding the model on a high level. The following equation describes the model on a high level. Simply, the model probability for a given storm is a function of storm environment, specifically instability and shear, and 3 observational predictors. In the model, the storm environment is characterized to a first order as a combination of instability and shear computed from the rapid refresh model. Observational predictors comprise 2 satellite growth rates and 1 instantaneous radar field. Because observational predictors drive the model output does not exist until clouds begin to develop. The model does not predict cloud growth, nor predict where a storm will move, but gives a probability a given storm will first produce severe weather in the next 60 minutes, wherever it may move. On the bottom right corner of certain slides, such as this one, you will see a supplemental training link. This link opens a web page with a bit more detail about the slide topic. A few more details about the input data into the statistical model are beneficial. The high-resolution numerical weather prediction data, currently the rapid refresh, are used to characterize the instability and shear of the environment in which the storm develops. Satellite imagery is used in 2 ways: to track clouds across space and time, in much the same way a human views satellite imagery loops, and to quantify the cloud growth rates, which are used as predictors in the model. Radar data are used in a manner similar to satellite data. The radar data are used to track storm cells in reflectivity imagery, again like a meteorologist looks at a loop of radar imagery. Radar data are also used to quantify the intensity of the precipitation core of a developing thunderstorm, which is used as a predictor in the model. A schematic of how the statistical model works is presented on the following slide, and then you'll see some more details on the input data sets. The following schematic illustrates how satellite and radar data are tracked by the computer, and how this all feeds data into the statistical model, without dwelling on the complicated details of satellite and radar tracking. First, we have a visible satellite image. A meteorologist doesn't look at this image and see pixels. A meteorologist sees cloud clusters, developing thunderstorms, etc. So it's necessary to train the computer to think like a meteorologist. The computer needs to identify cloud boundaries and track those cloud clusters and their evolution over time. The same concepts apply to radar data. Again, the computer needs to think like a human and identify storms or cells. And like with satellite data, the computer needs to track these storm cells and their evolution over time. So how does this all come together? This following animation is a 2D schematic representing a storm growing with time. The computer tracks clouds as storms or clusters like a human, while computing the satellite growth trends. Once a developing storm exhibits moderate reflectivity, the computer identifies and tracks cells in radar imagery. Once storms are tracked on radar, they inherit the parent cloud's satellite growth information, which information generally occurred earlier in the storm life cycle. Both the satellite growth rate information and the radar storm intensity information are input into the statistical model to derive the probability of severe weather. The computer continues to track storms in both satellite and radar imagery. The model continually updates probabilities as new observations become available. The storm environment information currently comes from the rapid refresh model. We use model information to make a first-order approximation of the storm environment, namely instability and shear. The environmental shear parameter used is the effective bulk shear, EBS. The EBS normalizes shear between storms with deep and shallow inflow layers and is more accurate when considering elevated convection. The environmental instability parameter used is the most unstable CAPE. The MU CAPE provides a generous estimate of instability. MU CAPE is useful for both surface-based convection as well as elevated convection. One important note about the NWP data used within the model is that we do not use a single forecast or a single analysis. We create a temporal composite and spatially smooth that temporal composite. Temporal compositing and spatial smoothing acts to mitigate NWP phase and placement errors in convective development. The last outcome we want is a poor NWP solution to squash model probabilities incorrectly. Surely, if strong convection is developing, there must be sufficient CAPE. The two satellite cloud growth predictors used in the statistical model are a normalized vertical cloud growth rate and a glaciation rate. How quickly a developing storm cools in infrared brightness temperatures is an indicator of severe potential. In the example over eastern Kansas, we can see rapid cooling in the imagery, and the computer quantifies this cooling rate, which is used as input into the statistical model. The cooling rate that is used is normalized. This way, seasonal and latitudinal differences in the cooling rates are automatically accounted for. The other satellite predictor used is the glaciation rate, or how quickly the cloud top is transitioning from liquid water cloud droplets, blue in the imagery, to ice crystals, orange, red, and gray in the imagery. Like the normalized vertical growth rates, the computer quantifies this information and how quickly a developing storm top transitions from water tops to ice tops is an indicator of severe potential. The radar dataset used is a multi-radar, multi-sensor radar products from the National Severe Storms Laboratory and the University of Oklahoma. The MRMS radar fields are a CONUS-wide composite of all individual NEXRAD radars. This is an ideal format for doing radar storm cell tracking. The MRMS data also fills gaps in single site coverage, including cone of silence, and offers increased sampling frequency when a storm is sampled by more than one radar. The radar storm cell tracking uses the MRMS composite reflectivity. The radar data used as a predictor in the statistical model is the MRMS maximum expected size of hail, or MESH. The MESH is derived from the Severe Hail Index algorithm, which is essentially a vertical integration of reflectivity above the melting level. So how is all this information combined in real-time processing? Unlike most GOES-R-related products that update with each satellite scan, the statistical model is different. This model updates at the frequency of the MRMS radar data, about every 2 minutes. When a storm develops and is tracked within satellite imagery, it has information about the storm environment from the RAP composite, which updates every hour. The probabilities are computed for every set of MRMS radar data, about every 2 minutes. The update frequency of the current GOES satellite is in routine scan mode is every 15 minutes, or roughly every 7 or 8 minutes in rapid scan mode. The critical point is this. The model does not wait on a satellite scan. It uses the most recent information available from satellite, whether the satellite is in routine scan mode or rapid scan mode. So users should expect updates in AWIPS2 about every 2 minutes. We will now switch from discussing how the statistical model works and learning about the input datasets to showing examples of how the model performed in some severe weather events. The examples will feature screenshots of the model output in AWIPS2. The model output is, by default, displayed in 2 ways. One is a probability contour with a color enhancement designed for overlay on top of typical radar reflectivity color tables. The shapefile nature of the output makes the display very flexible. The contours can be overlain on any field within AWIPS2, for example, satellite imagery or radar velocity imagery. Additionally, the model probability and each model predictor is displayed as text when sampling is turned on. The following bullets briefly describe the text readout. This field is the statistical model probability and ranges between 0 and 100% for a given storm cell enclosed by the color contour. This field is the most unstable cape from the RAP composite for the storm cell. This field is the effective bulk shear from the RAP composite for the storm cell, defining the storm environment. This field is the instantaneous MRMS mesh value. The time and value are provided. Note that the MRMS may not match a single site mesh algorithm, either the time or the value. The normalized vertical growth rate of the storm is the maximum value attained during the growth stage of the storm and the time that maximum value occurred. The units are percentage of the troposphere depth the cloud grew per minute. So a value of 3% would mean the cloud grew 3% of the tropospheric depth every minute, or 45% of the tropospheric depth over the course of 15 minutes. The exact values are not terribly important. We append a statistical measure of intensity with the terms weak, moderate, or strong. The glaciation rate is the rate at which the storm top transitioned from liquid water droplets to ice crystals. It is the maximum value attained during the growth stage of the storm and the time that maximum value occurred. The units are percentage of water to ice conversion per minute. So a value of 0.05 per minute would mean the cloud transitioned 5% of the water droplets to ice crystals every minute, or 75% of the liquid droplets converted to ice crystals over the course of 15 minutes. Again, the exact values are not terribly important. We append a statistical measure of intensity with the terms weak, moderate, or strong. While each model predictor is provided in the text readout, it is important to emphasize that the sum of the information, the probability, is more valuable than any individual piece of information. The examples on the following slides provide our take on how a forecaster may want to use the Prob Severe model output. But we don't have all the answers and need feedback, especially with the following questions. How can a forecaster interpret or use probability when it fluctuates over short periods of time, less than 10 minutes? Do rapid jumps in probability over short periods, again less than 10 minutes, to high probability values signify something unique about a storm? In some cases, high probability can exhibit as much as 60 minutes of lead time ahead of reported severe weather. how can forecasters use information when lead time is that large? The first example is over upstate New York in a region of marginal severe weather as depicted by the Storm Prediction Center outlook. Starting at 1944 UTC over upstate New York, MRMS composite reflectivity is shaded and the statistical model contours are overlaid on the reflectivity data with the text readout provided for the storm of interest. At 1944 UTC, a developing storm had moderate instability and sufficient shear to organize. The probability at this time was low, only 8%, as the satellite growth wasn't overly strong, in the moderate range. 15 minutes later, at 1959 UTC, the radar intensity of the storm began to increase, and the model probability increased to 28%. At 2014 UTC, again 15 minutes later, the radar intensity continued to increase, and so did the model probability, now up to 46%. 5 minutes later, at 2019 UTC, the model probability first crossed the 50% threshold. This means the storm is more likely to produce severe weather than not. Perhaps looking through the radar tilts of the storm puts you on the fence to take action or not. The probabilistic information can be used to increase confidence and increase lead time of issuing a warning. At 2039 UTC, probability is fluctuating as radar intensity fluctuates. Also at 2039 UTC, a 58 mile/hour wind gust was reported at the Rochester International Airport, 20 minutes after the model probability first exceeded 50%. The first severe thunderstorm warning was issued at 2052 UTC, 33 minutes after the first model probability greater than 50%. This was the only storm to produce severe weather in this time frame. Storms further west did eventually generate higher probabilities and also produce severe weather. So in this example, the probabilistic information could have been used to raise awareness and increase confidence that this storm would produce severe weather on a day when the severe threat was marginal. The next example is in the Kansas City metro area on the evening of April 9th, 2013. This example occurs at night and was within a slight risk region in the Storm Prediction Center outlook. At 2:04 UTC, a storm was developing to the south-southwest of the Kansas City metro area with strong satellite growth signals, moderate instability and shear. The probability at this time was 22%. 35 minutes later, at 2:39 UTC, the probability had increased to 42% as the radar intensity increased. At 3:04 UTC, the model probability exceeded 50%, coming in at 68%. Can a forecaster take their existing warning procedure and incorporate the probability to potentially issue a warning sooner? By 3:19 UTC, the model probability was in excess of 80%. 3 minutes later, the first severe hail report was received, 18 minutes after the first model probability exceeded 50%. No warnings were issued on this storm, and this was the only storm within the small arc of storms seen in the radar imagery that produced a severe weather report, and the only storm to have probabilities exceed 50%. This next example is in a region of marginal severe weather threat over south-central Iowa. At 1954 UTC, a storm developed over south-central Iowa with strong satellite growth rates, marginal cape, and sufficient shear. The probability was initially low, around 6%. 5 minutes later, at 1959 UTC, the probability increased slightly to 18% as radar intensity increased. 10 minutes later, at 2009 UTC, the probability was at 35%. And 5 minutes after that, at 2014 UTC, the probability is up to 60%. Radar is observing an intensifying precipitation core. Let's jump ahead 40 minutes to 2054 UTC. The model probability up to this point fluctuated between 50 and 65%, and now was 73%. Again, using existing storm interrogation methods, a forecaster on the fence between issuing a warning and not can use the probability to increase confidence to issue a warning earlier. At 2059, the probability was over 90%. The first severe wind and hail reports were received at 2059 UTC, 45 minutes after the first probability over 50%. The first warning was issued at 2103 UTC, 49 minutes after the first probability exceeding 50%. One question we received was, what would the model look like if we just used the NWP environmental information and the MRMS mesh information? Using the Iowa example, we ran the model with and without the satellite predictors. This slide demonstrates the satellite information is absolutely critical. The probability at 2059 UTC is considerably higher with the satellite data, 93%, than without the satellite data, 40%. But even more important is the lead time and increase of probability earlier in the storm life cycle. The model run with the satellite data generates probability over 50% at 2014 UTC, which certainly would grab someone's attention that this storm needs careful watching. The model run without satellite data is only at 12% at the same time and would imply little threat from this storm. The final example in this training is over Nebraska and Oklahoma on a day where a significant outbreak of severe weather was expected. Up to this point, the examples have focused on more marginal events because we believe the probability information might provide the most value in those cases. However, the probability information is still very useful on the more slam-dunk, moderate, and high-risk days. There are a number of storms on this day, but for now we'll focus on a couple over Nebraska. At 2044 UTC, storms developed in an environment supportive of severe weather and exhibiting strong satellite growth rates. The probability on the highlighted storm was 49%. At 2058 UTC, 14 minutes later, the probability had fluctuated downward to 30% as the radar intensity diminished. These fluctuations are more obvious when viewing the full-time updates every 2 minutes. By 2106 UTC, the model probability increased again. It's now over 50% for the first time, at 56%. 18 minutes later, at 2124 UTC, the model probability for this storm was now 75%. Using existing warning procedures combined with a model probability can allow a forecaster to consider a warning earlier. At 2136 UTC, the probability was at 90%. A tornado was reported at 2134 UTC, and the first warning was issued at 2143 UTC, 28 and 37 minutes respectively, after the statistical model generated probability in excess of 50%. Further southeast, another storm was developing at 2136 UTC with a favorable environment and strong satellite growth rates. At 2148 UTC, the model probability for this new storm was 53%. Jumping ahead nearly an hour, at 2240 UTC, the model probability was 82%. During the previous 52 minutes, the probability fluctuated between 45 and 65%, and then increased into the 80% range near 2240 UTC. This storm was tornado warned and produced a tornado with damage and injuries at 2245 UTC, 43 minutes after the initial probability over 50%. Again, a forecaster can include the probability into the existing storm interrogation techniques to increase confidence for issuing warnings earlier. On the same day to the southwest over northwestern Oklahoma at 2144 UTC, storms were developing along a cold front. At 2144 UTC, a developing storm exhibited low probability. Only 4 minutes later, at 21:48 UTC, the probability jumped to 54% as the MRMS mesh and satellite growth rates intensified. By 22:04 UTC, the model probability was 90%. This storm snapped power lines at 21:54 UTC and was first warned at 22:25 UTC. The lead time for severe weather for probability over 50% was only 4 minutes, but 35 minutes before the first warning. This example also illustrates one of the earlier questions. Does a rapid jump in probability over short periods of time to high values signify something unique about those storms? Specific storm examples are useful, both for gaining confidence in the statistical model and for seeing how the data looks within AWIPS2. This figure illustrates a quantitative validation of the model probabilities. The validation was for about 9,000 storms on 19 convectively active days during 2014. This figure shows the probability of detection, the false alarm rate, and the critical success index for both the most skillful model probability level, which was the 80% threshold in this case, and the National Weather Service warnings using local storm reports as truth. The probability of detection is 60% for the model and 68% for the National Weather Service. The false alarm rate is about 58% for the model and 44% for the National Weather Service warnings. Combined with the misses, the CSI scores are 33% for the model and 44% for the National Weather Service warnings. To no one's surprise, trained, experienced human forecasters are more skillful than the statistical model. However, in looking at the median lead time, the model provides 29 minutes of lead time to the first storm report, while the National Weather Service warnings provide 19 minutes of lead time to the first storm report. So the model has less but comparable skill, and it provides an additional 10 minutes of median lead time on the National Weather Service warnings. While the model performance is good, there are some biases that should be considered when using the model output. Current GOES contains 30-minute observation gaps every 3 hours, and storms that develop during those gaps will be under forecast as the growth rates are essentially washed out by the poor temporal resolution. Storms developing beneath thick cirrus shields or anvils are also generally under forecast. The reason being the model is essentially running with only NWP and radar information since the satellite could not observe the growth of the storm. Once developing convection transitions to linear modes, the probabilities will be under forecast. Again, recall the goal and design of the statistical model. It is the initial severe threat the model is designed for, and often, linear convective events are a result of upscale growth of initially more discrete convection. Storms that are only sampled by one radar may be under forecast or over forecast since the benefits of MRMS data are not gained. Lastly, a tornado genesis mechanism is not represented well in this model. A few other points to keep in mind when using the model probabilities. They are listed on this slide. This model will not give forecasters guidance on the type of severe hazard. This model will not provide lead time to every storm. Forecasters must still bear in mind environmental factors in addition to instability and shear. The model is designed and trained to provide the probability a storm will first produce severe weather within the next 60 minutes. The model is not designed to provide probability a storm will continue to produce severe weather, nor forecast storm decay. The model is most skillful and provides most lead time when the satellite can observe the development of the storm from immature cumulus to mature cumulonimbus. Currently, only GOES East is being processed. Forecasting severe storms is not easy. The statistical model is intended to distill gigabytes of data into kilobytes of useful information regarding the severe potential of developing storms in a clear, concise manner. It is important to re-emphasize the model will be most useful when incorporated into your current warning procedures and can help increase confidence in issuing warnings. On average, 1 to 4 NEXRAD volume scans earlier than would be done without the probability information. The details of the underlying statistical model, input datasets, and clouded radar tracking have been omitted from this training, but can be found in these references. The first reference specifically provides statistical model details and a more comprehensive analysis of the validation statistics. Please contact the statistical model researchers with questions, suggestions, etc. at the email addresses provided. To access this training online and access supplemental training material links from this presentation, please follow the URL provided. This concludes the probabilistic nowcasting of severe convection training module.